Dear students, welcome to yet another online tutorial on principles of communication system. So we have been discussing about sampling theorem. So in last session, we have seen in detail about sampling theorem, and we have even seen the proof, right? So what we have been discussing is, right, if you have a signal g of t, right, after sampling it every t a second, we will get the sample signal g delta of t, and we can represent it as summation n from minus infinity to infinity g of nts times del of t minus n ts. So this is how we'll represent sampling signal, sample signal, right? So in today's session, we'll see how to reconstruct the original signal g of t from this g delta of t, or the sample values. That's what we'll be seeing in today's session, right? So before that, right, we need some of the results which we have obtained in last session, right? So this g del of t, we found the Fourier transform of this g del of t to be equal to g del of f, and we found it to be equal to summation n from minus infinity to infinity. I told it can be n or m or anything, right? So I'll be using n, right? G of f minus n fs, where fs is actually what? Sampling rate or sampling frequency, right? And that is equal to 1 by sampling period. And where this g of f, right? G of f is nothing but what? Fourier transform of our signal g of t, and this in turn we know it's actually what? G of t is a band limited signal, so g of f will be a band limited spectrum, right? G of f, it will have maximum frequency content w, right, and so minus w. But this summation g of f minus nfs will be actually what? A train of this g of f's placed every multiples of fs. So if you are representing it, right, so it is, so of course it was weighted with fs. I forgot to mention that here, right? So this will be, this is how, right, say g del of f will be, right? G del of f will be like this. So this is 0, this is w, this will be fs minus w, so this will be fs, right? This will be minus fs, right? So on and so forth. So in this case, I have shown, this case which I have shown, it is actually what? Fs greater than 2w, right? Fs greater than 2w. We have seen if fs equal to w, these replicas will be just stitching each other. If fs is less than 2w, there will be overlap or aliasing. In that case, we won't be able to reconstruct or get back the original signal from the samples, right? That's what we have discussed, right? So now in today's session, right, what we will do is, from this g del of t, how can we reconstruct this g of t? For that, in last class itself we have discussed, right? If I can use so this will be fs by 2, right? This minus fs by 2, and this will be fs by 2. So if we can use an ideal low pass filter, right? If we can use an ideal low pass filter with transfer magnitude equal to ts, right, and which will allow from minus fs by 2 to plus fs by 2, we can get back the original spectrum, right? That we have, I have given an introduction in last class, so I request you to what? Please refer back to the last portion of the previous video, right? So like that, so if you have to reconstruct, right, the h of f, right, the reconstruction filter, right, reconstruction filter should have a transfer function h of f is equal to, it should be equal to ts from say mod f less than or equal to fs by 2 and 0 elsewhere, right? And we saw the inverse Fourier transform of this, or the impulse response, corresponding impulse response will be equal to sinc of fs t or it can also be written as sinc of, as Fs is equal to 1 by Ts, sinc of T by Ts. So we saw this, and then further, we have just came up with a model for reconstruction. So if we have the samples, the train of samples, then if you pass it through an LTI system with impulse response, h of t is equal to sinc fst, we will get g of t. This g of t is nothing but what? Sinc fst convolved with g del of t, right? This g of t will be sinc fst convolved with g del of t, right? So we'll see what exactly is that, right? So this g of t is equal to sinc, sorry, fst convolved with g del of t can be written as summation n from minus infinity to infinity g of n ts times del of t minus n ts. I can write it like this, right? And further, as we know, this convolution and summation both are linear operators. I can interchange them, right? So I can rewrite it as summation. I shifted the summation towards this left. So n from minus infinity to infinity, g of n ts I have taken as such, g of n ts into sinc of fst convolved with del of t minus n ts, del of t minus n ts, right? So if you observe this, this is actually what, convolution of some function with delayed impulse function, right? So you might have studied from the one of the properties of impulse function or delta function is, right? If I have a time domain function x of t, if I convolve it with del of t minus t naught, so del of t minus t naught will be del of t shifted right by an amount t naught, then the resultant will be equal to x of t minus T naught. So this is actually what one of the very important properties of impulse function, right? So what I've done is, if you are convolving x of t with del of t minus t naught, right? What we are doing is the resultant is x of t minus t naught, which means the t is replaced with t minus t naught. So wherever you have t in this expression of x of t, right, you replace it with t minus t naught. So basically it means, if you have an LTI system whose impulse response is equal to what, del of t minus t naught, that is actually what, a delta function shifted by an amount t naught, right? It will only cause actually what, a time delay for the original signal, right? That actually is the maybe interpretation of this, but right. So now in this case, our x of t is nothing but what, sinc of fst, right? So in this case, our x of t is sinc of fst, and instead of t naught we have actually what, nts. So if you apply this, right, to this, apply the result to our g of t, so our g of t becomes, g of t is equal to summation n from minus infinity to infinity, g of nts is g of nts as such, right? So sinc of fst, so what I should do is I should replace t with t minus t naught. So I should replace t with t minus nts. So it is sinc of, right, fs, it is already there, so t I should replace with t minus t naught. So it is t minus n ts, right? So I can write like this, right? So I can write like this. So this actually is called sinc interpolation formula for reconstructing the original signal, right? This is called sinc interpolation formula for reconstructing the original signal. If you, right, so the these very beautiful result, it's actually what, um, quite revolutionary. If it was not there, right, then entire digital communication, the stream itself wouldn't have been there, right? So so this is one way of stating it. Maybe what I can do is I can just rewrite this, right? So I can rewrite it. G of t is equal to summation n from minus infinity to infinity g of n ts times sinc of, right? If I multiply this, if I expand this, fst minus n times fst, fs is nothing but what, 1 by ts. So fs into ts will become 1. So I can write it as actually what, fst minus n, right? Think of fst minus 1. So in some textbooks, right, they have mentioned it like this also. These two are actually what, same. These two are same. I've just expanded it. So basically what happens is, right, so to get back original g of t from the samples, right, the samples, what we should do is, right, we should take sinc function, sinc of fst. So maybe I'll just write it here. So maybe the physical interpretation of whatever this mathematical equation I have written. So you have to take sinc of FST. So maybe what actually is sinc of FST? How can I represent it as graphically in time domain? That thing we'll see later. So you take sinc of FST. What you should do is you should shift sync of FST to all actually what NTSs, right? So for n is equal to 0, this becomes sync of FST itself. Then next you shift it to what, TS, 2TS, 3TS, so on and so forth. So shift it to shift to NTS, right? So it's both actually what, positive and negative shifts. But why? Because n spans from minus infinity to plus infinity, right? And apart from that, each shifted value should be actually what, scaled by the sample g of nts, right? Then scale by the sample values and add everything together, right? So if you do this, you will get back the original signal. So that is the meaning of this particular sync interpolation formula, right? So if you want to appreciate this, you should know what actually is a sync function. So that's what I'm going to discuss now, right? So normally sync function, so if I say sync of x, right, sync of x, it is defined as sine pi x by pi x. So if you plot this as a function of x, right? So for x is equal to 0, this will be sine 0 by 0. So, right, if you apply limit x tends to 0 for sine 0 by 0, you will get the value to be equal to 1. So that will be the maximum value of a sinc function that happens at x is equal to 0. Then you can see for every, when argument of sine has integer multiple of pi, it actually goes through 0, right? When the numerator is actually what, numerator argument of the numerator, right, or argument of the sine is integer multiple of pi, that is when x is equal to what, 1, 2, 3, or plus or minus 1, 2, 3, 4, etc., right? The numerator will be 0 and denominator will be non-zero, so it will be passing through 0. So maybe if I write it here, 1, 2, 3, right, and similarly minus 1, minus 2, minus 3. So a sinc function, right, it will have maxima, it will have maxima at and x is equal to 0, and it will pass through zeros at every integer values of x, right? So that is 0, 1, 2, 3, 4, or minus 1, minus 2, minus 3, etc. So this is actually what a sinc function, sinc of x. Right now what we have a sinc of fs times t, right? Or, right, sinc of fs times t is nothing but what, sine pi fst divided by pi fst, or else it will be easier if I write in terms of ts, right? If I write in terms of ts, right, it will become sine pi t by ts divided by pi t by ts, right? So of course for t equal to 0 it will have maximum, right? That's for sure. For t equal to 0 it will have maximum. Now we need to find for which values of t are sync of FST will have zeros, right? So for that, this pi t by ts, right? So for zero, what is the condition? The argument of the numerator, right? Argument of sign in the numerator should be equal to n pi. That is pi t by ts should be n pi. So this pi and pi gets cancelled, right? Which implies t is equal to n ts, where n will be from 1, 2, 3, etc. So for n equal to 0, it will be maximum, right? So the meaning is the sync function, sync fst or sync t by t, right? Or sync fst is nothing but what? Sync of t by ts, right? It will have maxima at time instance equal to 0, and it will pass through 0 every multiples of actually what? Ts, right? So that is actually the sync t by ts or sync fst, right? So I hope you understood what. I'll write it here: sync of fst or sync of t by capital Ts, right? So minus Ts, minus 2 Ts, so on and so forth, right? So this is actually what sync FTS. So now again we'll come back to our interpolation formula, right? Our interpolation formula says, right, g of t can be obtained from the samples, right, by the summation n from minus infinity to infinity g of nts times, right, sync of say, or I'll write fs times t minus n ts, right? Sync of fs times t minus nts. So what we have to do is sync of fst, right? Please don't have confusion by seeing like I've written it like this, right? So it just means I've, right, just explained it here, right? It means shift sync fst to every nts instances, right, both on positive and negative axis, scale it by the sample value and add everything together. That's right, add everything together. That is actually what the meaning of the summation, right? Multiplication with gnts is what I've written as actually what scale by the sample values, and this time shift, right? So in sync fst we have replaced t with t minus nts, which means sync fst should be shifted to every nts instances, right, both on positive and negative side. So you add everything together, that will, right, give you the original samples, right? Maybe now what we'll do is we'll try to what represent it visually. Suppose we have a message signal like this. Suppose we have a message signal like this. This is time instant 0, right? So that is not message original signal g of t, right, at time instant 0, and we are sampling it. So I'll just dilate the time scale so that you'll be able to appreciate it better, right? You'll be able to appreciate it better, right? Maybe I should. Okay, so I'll take another ink color so that, right, it's, maybe I'll use red color so that you will be right. So for instance, at time t equal to 0, this should be the sample, right? So at time t equal to 0, this is the sample, right? And say next sample I'm taking at, sorry, next sample I'm taking at time t equal to ts, right? Next sample I'm taking at time t equal to ts, right? Say this is that sample, right? At time t equal to ts, this is the sample, right? And next sample I'm taking at time t equal to 2 ts, right? So this is that sample time t equal to 2 ts, right? Then even on the negative time axis we do have that, right? So we'll have samples like this, right? Ts, right? So this is 0, ts, 2 ts, minus ts, minus 2 ts. Now what we have to do is, right, for n is equal to 0, it's actually what the this is actually G of 0, right? G of 0 TS, right? So for n is equal to G of 0 TS, so G of n TS at n is equal to 0 is this, right? N equal to 0 is this particular sample. So you have to, right, scale. Maybe I'll use another ring color now, right? So that you'll be able to differentiate. So which color should I be using, right? Again, I'll use a blue shade, right? Okay, right, yeah. So now, if I can represent it, right? So the sync pulse, right, corresponding to that it will be looking like this, right? I'll just expand it, right? And so what happens is only at time the first sync pulse, right? That is sync fs t, right? So what we need is sync of fs t minus n ts. So when n is equal to 0, when n is equal to 0, what happens? That becomes sync of fst. So sync fst scaled with g of nts, right? Sync fst scaled with g of nts. So instead of 1, the maxima will become actually what, g of nts. So this is the first sample, right? So next sample is actually what, g of ts times sync of, sorry, fs into t minus ts. Sync of fs into t, sync of fst shifted right by ts means it's actually what, shifted to this point, right? And right, so, and similarly in the next time instance it will be, right, this, and you can see the sync pulse corresponding to each sample actually what has maxima at that particular sampling instance, right? And it is passing through 0 in all other sampling instance, right? So if you add everything together, finally you will get back the original, actually what, signal. So this is the meaning of sync interpolation formula, right? Sync interpolation formula. So now in this session, what I have done is I have assumed a reconstruction filter, right, which is actually what, original, an ideal low pass filter, and using that idea we derived the sync interpolation formula. Instead of that, right, if you take inverse Fourier transform of say G del of f, right? If you take inverse Fourier transform of G del of f, right, if from minus w to w, if you integrate, right, this G del of f, e power j 2 pi f and ts df, right? This will again give you the same sync interpolation formula, right? That's what is done in your textbook. So I'm just leaving it for you to what, explore, right? So that's it about actually sync interpolation formula. So using the sync interpolation formula, basically I tried to, right, represent it graphically, right? So what basically happens, right? So sync interpolation formula is nothing but what, how to reconstruct the original signal from the sample value. So for that you have to take sync FTS, I'll repeat FST, sorry, sync FST, right? You have to shift it to what, each integer multiples of TS, right? Then scale it by the sampled value, then add everything together. So finally, right, if you add everything together, you may get the, so maybe I should be using another ink color to represent the, right, I'll use this particular ink color. Yeah, okay, fine. So if you add everything, the envelope of this will be our exact message signal if and only if, right, that condition is very important, if and only if this fs is greater than or equal to 2w. This is possible only when the sampling frequency is greater than or equal to 2w, right? If sampling frequency is less than 2w, you know there will be aliasing, right? And because of that we can't design a filter, reconstruction filter. An ideal low pass filter cannot actually what reconstruct it, right? So that's why this is true only when fs is greater than or equal to 2w. So in our textbook, what they have written is they have written this particular sync interpolation formula for the case fs is equal to 2w. So in that case, what happens is ts will become 1 by 2w. So shall we will just try and rewrite that sync interpolation formula for fs is equal to 2w, right? So or else, so this g of t, it will be equal to summation n from minus infinity to infinity g of n ts. So instead of ts, it should be 1 by 2w. So g of n by 2w, right? Then sync of, right, sync of fs into t. Fs, instead of fs, it will be actually what? 2w, right? Fs in sync of fs will be 2w, right? Fs into t minus nts. So instead of nts, it will be n by 2w, right? So this is one way, or else I can write it, right, by expanding it. I can also write it as g of t, it is equal to summation n from minus infinity to infinity g of n by 2w, right, sync of 2w t minus n, right? This is also possible. So both of these are actually called interpolation formula for reconstructing original signal from the sampled values, right? So and I just tried to visualize the physically what is meant by that mathematical expression, right? So and one more thing, what I told us, you can obtain the same result, right, by um, finding the inverse Fourier transform of g of f, and we know g of f is nothing but what? G delta of f from minus w to plus w. That aspect I have discussed. So maybe as a note, I'll post that in our canvas, right? So I'm not going to discuss that, but this method, what I have used now, is actually what a straightforward method. The other method also would be fine. So that's it. That's all about sync interpolation formula and reconstruction. So we'll wind up this session now at this point, right? So maybe in next class we'll see about pulse amplitude modulation and other aspects of this particular module. Thank you so much.